Yeah, so as have I introduced, today I'm going to talk about the uh, old but new story, FlowerTune. So it's a cross-domain benchmark for LM federated fine tuning. Yeah, so as we all know, the LM got remarkable performance on different domains and tasks. And to get better performance, what we have to do is to fine-tune the LM on a specific domain-specific data. But some research has shown that we are running out the high quality public data set. And on the other hand, the demand for the specific or the specialized LM is increasing. So for example, the domain like the medical and finance. And in these domains, the data that we can't get access to because it's under some regulation of privacy protection. So to achieve this issue and boost the performance of LM fine tuning, the potential solution is let's do federated LM fine tuning. So that's why FlowerTune exists. So here's a storyline that I want to walk you through today. So let's start with a template. That means we build up usable templates. It's called FlowerTune, and people can use that for any like a federated element fine tuning tasks. And build on top of that, we launched the Flower Tune LM leaderboard, so which have various baselines. People can test with different methods to boost the performance. And after that, on the top of the results we got from the leaderboard, we have a benchmark capability to have a benchmark in a unified setting to say so how the different model performed in FL settings. So the momentum to push these things moving forward is come from the Flower community. So now you may let's start from the first part. So you may already hear about FlowerTune tools, but let me just briefly remind you what it is. So FlowerTune is a bundle of techniques to make the federated element fine tuning easy. So it includes like the Flower data sets to produce and partition the data, and also it has an easy pre-trained LM adaptation. That means you can take any out-of-box pre-trained model and do the fine-tuning. And we also apply like the PEFT technique for faster training. For example, LoRa is could be used in this process. Apart from that, we also apply like quantization techniques for further speed up. And for the final thing is the Flower simulation engine or runtime. So that could be used to simulate the LM fine tuning, but of course you can do that on a real distribution settings without changing the code. So all come together that make the federated element fine tuning can be done with just a single GPU. With these tools, we just put the things together into a template, and you can just easily use that template by running this single command. It's Flower new and pass the parameter framework equal to FlowerTune. All right, so built on top of this usable FlowerTune template, we launched the FlowerTune LM leaderboards at the end of last year, aiming to like establish like various baselines for different domains that people can easily follow. So it includes four domains. So it's a general LP, a finance, medical, and coding. And at the first stage, you can round LM fine-tuning, federated fine-tuning on different domains. After that, at the second the stage, we provide the corresponding evaluation tools to uh, uh, evaluate the fine-tuning model and give a score to see how good the model is. So yeah, so it's a community effort as we mentioned, and so far in the Slack Flutter LM leaderboards channel we have 95 people, and people was quite active by asking questions, exchange ideas, and also running the different methods to do the LM fine tunings. And after launch, so we already got many submissions and tested with like different base models. So as we show here, including some popular model like Gamma, Llama, and also DeepSeek. Yeah, so that's what we have achieved. So in the current status of the LM leaderboard, we have got boosted performance for all domains and tasks. So that's two highlights. For example, in the general LP task, we have 5.6 times increase in terms of the evaluation performance. And the second one would be the finance. If you see the finance task, we got around 100 communication cost decrease in this task. All right, so we build on top of the LM leaderboards. So we have various uh, uh, results for different models already. So now it's time to have a benchmark to say, I mean, in a unified setting to see how the model performs in a federated setting. So that's something that no people did before, but it's quite important for the federated LM fine-tuning domain because people so in the different settings, people need to choose the proper model for to do the specific task. So that's why we want to do this benchmark. And there's some highlights. So it's the first kind of first of its kind benchmark to do the 26 LM, the pre-trained LMs on four domains, and we have the various evaluation benchmark, the evaluation metrics and the data sets. So thanks to the capability from the leaderboard. Yeah, so in terms of the FL settings, so we have a unified setting for all models, try to fairly compare the performance of them. So here, for example, we use the LoRa or Dura methods for the local fine-tuning, and after that, we only transmit the LoRa layers to the server, and then we aggregate them on the server and send that back to the clients and check the next round of FL training. So now let's see some results. So here we showed the average training loss over FL rounds on the four challenges. So you can see that so we have six selected model here. If you check, for example, the general LP task, you can see yeah, so the training loss going down is good, but also the high so you see the model here with different model size. So if you see this the general LP task, it could be the higher sorry the larger model would have the lower loss as expected because you know the larger model would have a higher capability to learn things. But at the same time, if you see the finance task, um, it seems that the model, you know, didn't show like much difference in terms of the training loss. The one reason for that is for the finance data, so the finance task, we only do the classification task. It will be easier for the smaller model will be enough sufficient for this task. And as for the evaluation metrics, so here we choose the three metrics apart from the downstream task. Uh, and in the downstream task, we use zero-shot settings. That means we fine-tune the model in federated setting and just take the train model doing the inference on the downstream data set directly. So that will be challenging, but also fair to say the model performance directly. And apart from the downstream tasks, we also have two systematic metrics, which are the communication cost and the memory consumption. So we think it is also important to show that because in FL setting, some scenario environments will be resource constrained. So that means maybe not everyone could afford the large model, and also for the different domains, the model would shows different behaviors. So that's why we have the multiple metrics here. So now let's just pick one of the domain to show the experimental results, how the model works. So here, the table shows the models in the finance domain, the finance challenge. Um, Here we in the different lines show the different base models, and the columns here shows the performance, the accuracy on different downstream data sets, and it also shows the communication cost and the memory cost in the last two columns. So there's some highlights here. So first, if you see this, the first two models, which are the largest model, it has the highest the accuracy as expected. But on the other hand, the communication cost and memory cost are also high. And another interesting finding is that if you see the smaller model, the small LM, we see that it actually gets some acceptable performance um, compared to for example, some larger model. This so as I just briefly mentioned, it's probably because in the finance challenge we only do some classification task, and the smaller model would have the ability for that. So this is good. We can use a small model for this task, and you see in the small model we have the very low communication and memory cost. Yeah, so you may already found that there's a trade-off between the accuracy, the performance, and the metrics. So here we have a figure to show this trade-off. So this figure shows the same task, the finance challenge, but we just split into the two subfigures, which are the communication and the memory. And yeah, you see that, for example, this point is for the Gamma 9B model. It's get a good performance, but also still it has the higher, the systematic performance. On the other hand, for example, this blue lines and points here show the smaller model. It has a lower performance, but also a lower the communication cost and memory cost. Yeah, so we just in this talk we just want to showcase some uh, examples of the experiments, but there's indeed more interesting results in the paper. So yeah, please go to the paper to check more details about this. Okay, so Flutter LM leaderboard is still open, so we open for more submissions. And also at the same time, we want to have like more scenarios and more modalities, and we also target to have a more realistic FL settings. So if you are interested in joining this initiative, so please scan this code to join the Flavor Slack channel and jump to the Flavtune LM leaderboards yeah, channels. And also, if you want to check out the more details about the paper, so here's the paper link. Okay, so that's it for today's talk. I want to take a chance to thank so every contributor in this Flavor Turing paper coming from Flavor Labs and Flavor community. Thank you.
Thank you, Jan. I think it was super interesting presentation. I also echo the thanks to the big community that has been making this possible. Thanks to, I think I was counting now, like around 80 submissions that made it to the leaderboard. That's quite something, especially that federated learning is still has so much to grow as a concept in AI. I have one question. So in one of your last slides, you were saying, well, there, maybe we could introduce other modalities or maybe more realistic setups. How would you make the setups in the evaluation particularly more realistic? Is it more about introducing more partitions, like more clients, or is it more about introducing new data sets? What are your thoughts?
Yeah, so thanks for the question. Yeah, I think this is a good question. So we for the more realistic settings, I think it will come from two aspects. So first one is so just as you mentioned, the number of clients. I think the current setting is more like the cross silo setting. So that means the number of clients is not that high, but we can also do the cross device setting. That means we have more clients, but we also have a more strict resource requirements. Uh, so that will be one. And the other thing is the data distribution of the clients. So um, we can simulate somehow a more realistic setting, for example, to simulate the no ID setting, which will be quite common in the real world.
Yeah, makes sense. And among these four, so there are four leaderboards, I think general NLP, medical, finance, and coding. Which of these modalities do you think has maybe the chances to have a much bigger impact? Or
Everyone.
do you see one of them getting people more excited from your interactions with the community?
Well, I think I'm not sure which one will be get better impact, but I hope every challenge will to get like a more attractive for different type of groups. It's quite separate topics, and the people doing that maybe from the specific domain, and they are only interested in the specific topics that they are working on. So hopefully, yeah, every challenge could get more attraction. Yeah.
And for you, which one is the most interesting?
Most interesting.
For you, yeah.
To me, I think the medical and the finance one to me is more interesting because you know and the data type is quite I say it's realistic settings when people in these domains really has this demand to do the federated element fine tuning. So yeah.
Yeah, I agree. I think those two are quite important ones. Okay, amazing. Well, Jan, thank you very much for your presentation and thank you also for everyone that was included as an author on the paper or that made a submission to the Flower LLM leaderboard.
Thank you.
So let's jump to our next talk. It's going to be about, it's titled Federated Learning with the Flower Framework, a collaborative approach from the Euclid team. And it's going to be delivered by Eleni Briola from the Danish Meteorological Institute and Christos Chrysantos Nikolaidis from the Democritus University of Thrace. I'm really looking forward to know what the Euclid team is. So the floor is yours.
So I will start sharing my screen.
Yeah.
Do you see it?
Yeah, perfect.
Nice. So, hi everyone, and thank you very much for the invitation today. We're really excited to be here. I'm Eleni and I'm joined by Christos. We're both part of the Euclid team. It's a research unit working on responsible AI based in Xanthi, Greece at Democritus University of Thrace. In this presentation, we'll walk you through how we've used Flower in different federated learning projects, from healthcare to social care and privacy research. Flower has really helped us explore a range of real-world scenarios in a practical and scalable way. So let's get started. Just to give you an idea of what's coming up, we will start with a quick introduction to our team and what we've been working on, especially how we will be using Flower framework across different projects. Then we'll walk you through 3 case studies, one about breast cancer classification with explainable AI, another on predicting when elderly users might drop out of health apps, and the third focused on improving how we pick clients in the federated setups. After that, we'll spend a bit more time to our latest and most exciting topic, membership inference tags. And this is where we dig into the risks around privacy and how we can defend against them in the real-world settings. And we'll end with some final thoughts and key takeaways. Hopefully, this will give you quite a good sense of what we were working on. So here is our team. This is the Euclid Responsible AI Research Unit. It is based in Democritus University of Thrace in Xanthi, Greece. Do you see the next slide or not?
I don't see it, no.
So is it in the first, in the second, in the third one?
We are in the first slide. Oh, now I can see the team.
Nice. And when I say change now, can you see the second slide?
Overview now.
Nice. So, okay. So here's the team. This is the Euclid Responsible AI Research Unit. At the top is our head researcher, Pavlos Efremidis, who guides the overall direction of the group. Then we have our associate researchers, Vasilios Perifanis and Georgios Rosatos. And finally, we're lucky to have a strong group of PhD candidates, all of us working together on projects around federated learning, privacy, blockchain, responsible AI. It's a very collaborative team. And a lot of what you'll see here today is a result of joint efforts across different backgrounds and strengths. So I suppose now you see the next one, right?
Yes, I think it's working fine now, yes.
Nice. So here is a quick look at what we do as a research unit. Our work covers a range of topics, from algorithms and federated learning to privacy, explainable AI, blockchain, and even the intersection of AI with sustainability. So it's a pretty broad space, but all with a responsible AI focus. On the right, you'll see some of our impact so far. We've published over 100 research papers, earned 4 awards in competitions, and have been part of 6 national and EU-funded projects. And we're not doing this alone. We collaborate with several universities, research institutions, and industry partners, both in Greece and internationally. And these partnerships help us take our ideas from the lab into real-world application, which is something we really care about. So before we dive into the projects, here is a quick intro on who we are. I'm Eleni. I work as a machine learning scientist at Danish Meteorological Institute, but I'm also still a PhD candidate at Democritus University of Thrace. My work mostly focuses on scalable deep learning, federated learning, and how we bring all of that into practical use for things, for example, in my work like weather forecasting. I'm also really passionate about science communication and working across different disciplines, and I like solving real-world problems. I will hand over to Christos as well to introduce himself in order not me to do it. if he wants to say a little
Okay,
things about him.
I'm Christos. I'm PhD candidate at Democritus University of Thrace. I have 2 masters, and I'm research is distributed learning and privacy enhancement technologies. I'm focusing on members in FIFA attacks, and I experience with secure multi-part communication and homomorphic encryption.
Nice. So this is the team behind the work you'll see today. Before we jump into the specific studies, we just wanted to highlight how central the Framework framework has been to our work as a team. That's why we were also really excited when we conducted and making this talk here today. Whether we are working on breast cancer classification, predicting dropout, or trying to understand and defend against membership inference attacks, Flower has been the tool we've kept coming back to. It gave us the flexibility to try out different strategies, from custom client selection to privacy-preserving techniques, and made it easy to run responsible experiments across different setups. So in all the projects you'll see next, there is one thing in common. They all built in using Flower. So this is the first study. I have put all of the QR codes in order if you want to check out each study. So in this study, we've looked at how we make breast cancer diagnosis both accurate and explainable without compromising patient privacy. As you know, medical data is extremely sensitive, so using centralized AI approaches can be risky. That's where federated learning comes in. It let us train models without actually moving the data. We used Flower to coordinate the training process across clients, and we worked with 2 datasets, the Wisconsin Diagnostic Breast Cancer dataset and Wisconsin Breast Cancer dataset. What makes this work stand out is the use of SAP-based explainability within the federated setting. So what we did, we combined either neural networks or XGBoost models, and in each client, we computed their own sub-values locally. So this setup allows us to keep data private while still understanding how the model decisions were made, something that's especially important in the clinical context. Let's talk now about what we found. The results were really strong. Accuracy and F1 scores were very close to centralized models, going up to 98.39%, which is great, especially considering the data never had to leave its client. Also interesting was the fact that when we aggregated the sub-values, we saw consistent feature importance across clients. This means that the model was not only accurate, but also explainable in a reliable way without compromising the privacy. With Flower, we made all of this possible. It allowed us to use different types of models like ANNs and XGBoost and easily plug in our explainability pipeline. So overall, this work showed that federated learning doesn't have to be a trade-off between privacy and transparency. You can have them both. The next study is about a really important and often overlooked challenge, user dropout from health aging apps. These tools are designed to help older adults stay engaged within their health, but when people stop using them, the long-term benefits disappear. So at the same time, the data generated by these apps is personal and sensitive, so we need to be really careful how we handle this. That's why we used federated learning with Flower. It allowed us to train models directly on the client side without even moving the raw data. We tested several settings in both IID and non-IID settings to better reflect the diversity in user behavior. What stood out was that the federated learning actually performed better than centralized versions when it comes to F1 score. And with Flower, we could easily simulate different client environments and explore how personalized strategies work across the board. So this work really shows how federated learning and Flower in particular can help us build digital health solutions that are both personalized and privacy-preserving. And in connection to that, this study takes things a step further. So we're still focused on predicting dropout from elderly care apps. But here the question is, how can we do even better by being smarter about which clients participate in training and how we deal with imbalanced data? So again, the data is sensitive and decentralized. So we worked in a federated setting with Flower. But this time we tested 3 client selection strategies, picking clients to balance label, prioritizing the ones with more data, and the combined approach. So on top of that, we tried oversampling, undersampling, and a hybrid method to fix class imbalance. And what we found was quite promising. With the balanced client selection strategy, we reached an F1 score of 76.4%, which was 13.5% better than the centralized baseline. And even more impressively, we slashed training time and emissions by nearly 89%. So Flower made all this possible and gave us fine control over client selection and let us test our custom strategies in a reproducible way without compromising on privacy. And in short, this paper shows how federated learning isn't just about privacy. It can also deliver better performance and be more sustainable, especially when paired with the right strategies. So this was from me, and now I will give Christos to take it from here. What I did was a quick tour, as long as Christos trying to share, of our recent projects, what we used, and to tackle with real-world problems in healthcare and social care apps, from breast cancer to improving elderly care. And we're trying now to shift the gears and dive into our latest work, which focuses on membership inference attack. It's a serious privacy concern in federated learning. And Christos, nice.
Do you see it? That's okay. Let's
Yes.
go right. Okay.
Nice.
Okay. So I think you see my screen now.
Yeah, all good.
Okay. So hello everyone. We presented my recent research on membership inference attacks in healthcare application. So federated learning is often promoted as a privacy-preserving alternative to centralized machine learning, especially in sensitive areas like healthcare. The assumption is that because data never leaves the client, privacy is preserved. However, this is not the full story. Even without sharing raw data, model outputs can leak sensitive information. So in this work, we focus on membership inference attacks, where adversaries try to infer whether specific data records or even entire clients participate in training. We explore this threat both at the record and client level to give a more complete and complete picture of FL's privacy limitation. So this diagram shows the standard shadow model pipeline used in membership inference attacks. We train multiple shadow models, datasets that simulate the original training data distribution. For each shadow model, we know which records were used in training and which were not. So we collect the output predictions for both sets and train an attack model to distinguish between member and non-member behavior. Once trained, this attack model can be applied to outputs from the real target model, allowing us to infer if a specific record was part of the training without even seeing the raw data. This approach is both effective and realistic, making it a meaningful threat to privacy. On the left, we see the configuration of our target model, a simple neural network with 3 dense layers, ReLU activations, dropout, and schismoid output for binary classification. It was trained using Adam with a learning rate of 0.001 and batch size of 32. In the middle, we summarized the federated setup. We ran 20 rounds and the client training locally for 10 epochs. And on the right, we note that the shadow models used by the attacker following the same architecture as the target to simulate the gray box attack. So to train the shadow models, we simulate 2 types of attackers. On the left, we have a strong attacker who has access to real data, specifically from 5100 or 150 clients that were not included in the target model training set. On the right, we simulate a weaker but still realistic attacker who use CPGAN to generate synthetic data that mimics the real distribution. SID-GAN was trained on the real client data and was used to generate new samples that approximate the same distribution. This step allows us to evaluate how effective MIAS can still be, even when the attacker has no direct access to the real training data. Here's how the attack works in practice. We feed either individual records or full client datasets into the target model and collect its output predictions. These outputs are passed to an attack model, which is trained to predict membership status. At the record level, the goal is to determine whether a specific data point was used in training. And on the client level, we ask whether the entire client participated in training at all. So to make that decision, we aggregate the attack model predictions across all samples from a given client. And then we compute a membership ratio, the proportion of samples predicted as members, and we compare it to a threshold. So if that ratio exceeds the threshold, we classify the client as having participated in the training. Here we present the result of our record level MIAS, evaluated using the F1 score. On the x-axis, we see the 8 training configurations. CL stands for centralized learning. FL refers to federated learning. FLCL is federated learning with client selection, and FLTP is federated learning with differential privacy. So each configuration was evaluated using either real or synthetic shadow data. And we also varied the number of shadow models, showing by the different color bars, 1, 2, or 4. And some few key observations. Centralized learning with real data was the most vulnerable setup. With 4 shadow models, the F1 score reached up to 85%. Federated learning reduced this vulnerability, but attacks still succeed, especially when the attackers use real shadow data. Client selection improves protection by reducing the consistency of client participation. And of course, differential privacy provides strong protection across all setups. Finally, using synthetic shadow data reduces the success of the attack, but does not eliminate it. Overall, the attacker's resources, particularly the number of shadow models, have a direct effect on how successful the attack is. So this summarizes our threshold tuning procedure for client-level MIAS. For each threshold, we check how many of a client's records are flagged as members by the attack model. If that proportion exceeds the threshold, we classify the clients as a participant. We repeat this for all thresholds, evaluate its performance, and select the one that maximizes the F1 score. So this job is simple but powerful, and it significantly boosts attack success. These are the results from our client-level MIAS. Each upload shows one training configuration. We compare fixed vs tuned threshold strategies using 1, 2, and 4 shadow models. The key findings is that threshold tuning consistently outperform fixed thresholding, especially in centralized setup. In centralized setup, tune F1 scores goes as high as 78%, showing strong attacker success. Federated learning setups are more resilient, particularly with client selection or DP, differential privacy. And of course, synthetic shadow models lead to lower scores, but attacks still works. Overall, the tune approach makes client-level MIAS much more effective and reveals the gap in federated learning defenses. So to summarize, centralized models are most vulnerable, especially with strong attackers. Federated learning helps, but not eliminate the leakage. Client selection limits participation and weakens the attacker signal. And threshold turning is a simple enhancement that significantly improves client-level MIAs. And while synthetic data offer moderate protection, it is not enough by itself. So effectively, privacy in FL requires multiple layers of defense. And some conclusions of all our works. Today we saw how federated learning allows us to work with sensitive data, like medical or social care data, without even needing to centralize it. That's huge advantage when privacy is not negotiable. The Flower framework made it possible to run all kinds of experiments, whether we were focused on interpretability, like with SAP, or in smarter training setups like client selection or privacy attacks. Across everything we explored, three themes stood out: flexibility, privacy awareness, and reproducibility. So Flower provided the tools to deliver on three. This is references for our works, and thank you so much.
Great. Thank you very much, Reni and Christos. I think it was super good presentation. I have a couple of questions, but if somebody else in the audience, either on we are live now in many places like X, Twitter, YouTube, even here on Zoom. So if anyone has a question, feel free to write it in any chat you have at hand, and I will try to read it. But in the meantime, I have a couple of questions. Maybe I can ask. I mean, either of you can answer, but for the first part, I was curious about what is the federated learning setup you had. Like, for example, what were the number of clients? You were saying that, Eleni, that you were evaluating both IID and non-IID setup. So, for example, for non-IID, how did you evaluate a non-IID setup? You had the data and then you decided how to split it between different clients, or you had already some kind of patient ID and you can follow a natural distribution. Do you have something to share there?
I think also Christos can answer this question. Basically we have data from different sources. So it's not like the regular machine learning that you have data from a specific source. So we have data from different sources and we try to combine them. That's why we said that we had non-IDs as well, non-IID data as well. But I think, Christos, we can also elaborate on this since you continue the work.
I agree. We have a variety of data, and that's why we speak about non-IID.
Yeah, makes sense. But then when you were doing the experiments, for example, and then let's say you have 5 sources of data, that would mean that each of your clients only has data from one of such sources, for example?
Yes, we have a lot of process to make data from for clients, and yes, we have a different data, so we combine them with a federated learning task.
Okay, makes sense.
So each client had different kinds of data. One client had, for example, one type A data and the other type B data. So
I understand. Okay.
From different sources.
Okay, cool. How were you running the experiments? Were you using, for example, the simulation engine in Flower, or were you setting up a real federation with the deployment engine? Do you have
We try the simulation.
simulation? Okay, cool.
Yeah.
That's good. That's perfect, actually.
Yes, I think in all experiments we had the simulation only.
Yeah. I think many times for doing most of research, I think simulation is pretty good.
Yes, it's easy, it's pretty good, it's go with the flow, it's okay.
Okay, cool. There was one part, I think, Christos, in your results, where I saw, so we could see like having 4 shadow models was consistently resulting in better F1 score. Maybe I didn't understand everything about the shadow models, but is there a trade-off? Is there some other trade-off of having more shadow models? Like, is there a drawback of having more shadow models?
Yes. The base idea is that if you have more shadow models, we have more data to train shadow models. If the shadow models see more data, in principle, it is more stronger. But the data is the data has to be good to work this on. It's not about the number of shadow model, it's about the data that the shadow model sees. But in principle, if we have a lot of shadow models, the ME attacks is getting better.
Okay. Interesting. I'm checking if there are some questions. I don't see questions here in the chat or in the other sources, but I think that's fine. I saw that for the first work, there were a couple of, at least one publication that I could see it online for this this MIA work. Is there also a paper related to it?
Yes, of course.
Okay.
We are our last paper.
Oh, right. Yeah. Okay.
And see the paper.
Amazing. Is there an open source repository for this?
A few weeks ago. It's published a few weeks ago.
Okay, GitHub. Okay, amazing. Okay, great. I think maybe then we can thank you very much for your talk, Christos and Eleni. I think we can give next turn our final speaker. So I'm gonna share my screen. Yeah. So that was a talk from Eleni and Christos. Super interesting. And now our final speaker is Chen-Rui Fan from the University of Bern, and he's going to tell us about federated learning in multivariate time series for data distillation. So, Chen-Rui, the floor is yours.
Hello.
Hello.
Can you see my screen?
No, we cannot see your screen.
So you cannot see my slides, right?
No. Can you try sharing again?
Okay. Still not yet? Okay.
I can see it then. I can see them. Perfect.
Yeah. Thanks for Flower AI that invited me to do this presentation to introduce our work, the federated time series generation on future and temporally misaligned data. So this work is done by me and my coworker and also a coworker from University of Bern, TU Delft, and also from the Neuchâtel. So yeah, so let me start. So let me start with a quick motivation of why time series generation is hot in federated settings. So time series data is fundamental to many real-world applications, such as patient monitoring in hospitals and the financial trend analysis and the industrial IoT system. So in many of these settings, different organizations like hospitals or banks cannot share raw data due to privacy laws or competitive concerns. Then we know that federated learning is a promising solution because it allows us to collaboratively train models without centralizing data. But however, in practice, federated time series data is rarely clean. That's why. That's because first, feature misalignment occurs when clients select different subsets of features. And for example, like in there's two hospital A and 2, and the first hospital only record blood pressure and temperature, but the second hospital record like heart rate or other information. So like here, the client one, could you see my mouse, the cursor?
Yeah, we can see it, yes.
Yeah, okay. So the client one only have the feature A, B, C, and the client two have the A, B, D, E. So in the feature level, they cannot align. And the second, temporal misalignment is common because clients collect data over different time periods or at different sampling rates. So for example, here, this client 1 from 16 to 744, but client 2 from 2000 to 3000 and so on. So this is another problem. So finally, missing values due to sensor failure, which is very common in the time series. So this is very different from the tabular data with the time series. So to solve this, to the 3 problems, we need to think about some methods. So in our setting, so each client is on time series data, but they differ in 2 important ways. First, the time window are misaligned. One client might collect data from 16 to 744, one from another time step. There's no common time axis. Second, the feature sets are not the same. So one have some data, but not some other ones. And also, maybe we can collect some public data from the public data set. And in the public data set, there is feature A and B. That is, we can call it common features. But there is some other features that only the client itself have, like the feature F, feature C. Those features are very private. They don't want to share it, so they cannot do the feature alignment. So these issues, feature misalignment, temporal misalignment, and also the missing data, make the collaborative generation in a federated setting extremely challenging. And why we need to think about a new method to solve this. Let's look at why existing federated generative models fall short in a real-world time series setting. So there is a few methods, and the vertical FAL models like the GTV and the DGP-DAN assume that all clients share the same samples or time steps, but have different features. So they handle feature misalignment, but not temporal misalignment. Horizontal FAL methods, such as the FATGAN and the times-to-times GAN, assume clients have the same features, but different samples, meaning that they can address temporal misalignment, but not feature mismatches. Then the VFL GAN TS is also vertical and can handle feature misalignment, but again assumes aligned time steps. So none of these methods are designed to handle both types of misalignment, especially in the presence of missing values and strict privacy requirements. This is a gap our method, FAT-TDD, aims to address. So then we share our new method, the FAT-TDD. Oh, sorry, the federated learning in multivariate time series via data distillation. So to address the challenge of double misalignment, we introduced FAT-TDD, a hybrid federated learning framework that uses diffusion models in a novel way. So instead of sharing the model parameter or even the real data, we share the synthetic data, synthetic common features, which still allowing knowledge transfer. The framework has 2 main modules. First is about the distiller. The global distiller trained on public dataset and also on the synthetic outputs, learning to impute missing common features. And the second, the imputer to reconstruct its exclusive features guided by the improved common features. This process repeats over multiple rounds. The distiller gets stronger, and in turn, each client can better impute its local data. And I will introduce each module step by step, so don't worry about this structure. So in the first step, is this blocking? Okay. The first step, the coordinator uses a publicly available dataset that contains only common features. So you can see here, there is a blue feature and the orange feature, right? So we can call it A and B, and they exist in the public dataset. Then the distiller will train on this dataset that it learns to reconstruct the clean time series by reversing added noise. So you can see it is a traditional DDPM training framework. Then after we got the distiller, we will distribute the trend destiner to each client. Then each client will get the destiner locally. And what's next? Destiner, each client now runs the destiner locally in a backward delousing process. Given partially observed common features, the destiner fills in the missing values through conditional sampling. So this step ensures that each client have a complete versions of A and B. So let's look at the graph. So you can see there is a blue and the orange, and also the green and red features, right? Up to the destiner imputation, we have a complete blue and orange feature, but the red and the green is still missing. But don't worry, we will find out how to deal with them. And the fourth step, in this step, each client uses the complete common features A and B, and as an auxiliary input to impute the missing exclusive features. So why we call it is auxiliary input? Because those are the synthetic data. Yeah, you can see those imputation is some synthetic data, but these have some information from the public dataset. So the distiller is trying to transfer the knowledge from the public dataset to each client. Then each client can use those information to do the imputation of on the green and red time series. So yeah, once these values are imputed, we combine them with the real data, and then we initially apply the untrained local imputer to get a first pass estimation. So this is initialized with random weights. In our settings, we initialize this with the pre-trained model. Then we got the imputer, and we do the first pass to get the complete synthetic time series. And we combine it with the real data. And then we got this, and we use this to train the model. So after the training, the imputer is used as a generative model. Each client samples from noise and decodes into synthetic time series that include both shared and private features. This synthetic data acts as a proxy to share knowledge without exposing raw samples. So you can see here, the imputer after training, it can generate some synthetic data here, but it also have both have the common feature and also the private feature, the exclusive feature. So we can see the problem, we don't want to share the private feature. So what do we do? For privacy protection, each client only shares the synthetic values of common features like A and B. No exclusive features are sent, and no raw data is leaked. The coordinator then merges these synthetic common features into its public dataset for the next round. Then, each client sends the data to the public dataset. Then we have a new public dataset right after one round. And in the next round, the destiner will fine-tune on this dataset and get a new weights. And it will do this again, distribute its weights to each client and do the imputation again. And the imputer will also do the imputation and train on the new synthetic dataset, get a better weights. So that's all is about our structure. And about the experimental setup, we evaluate our framework on 5 datasets from diverse domains. Stocks and energy are financial and environmental datasets with seasonality and correlation. Musical comes from simulated physics, while fMRI is a highly complex brain signal dataset. For metrics, we use the context FID to measure global similarity between real and synthetic data, and the correlation score to assess whether relationships between features are preserved. We also include the discriminative and the predictive scores to test the realism and how well synthetic data can support downstream forecasting tasks. We compare against the 5 baselines include local owning and centralizing training as well as pre-trained model using public dataset. So let's see the result. I need to explain the settings. You can see here, there is a file method. There is two centralized, one without, one without. So the first one is a perfect case. I mean that if there is a hospital, a company, or a cluster, a server, coordinator, or anything, they have all the features and there are no data missing. Like they have the data set, have feature A, feature B, feature C, and D, and there is no data missing. The perfect case, they don't need the federated learning, right? So they have the best results. And the second centralized means that we need to do the federated, but we can't. We only have feature A and B, and there is some data missing happens. So you can see the result is very bad. And local means that each client just train locally, do not do the federated learning. And the pre-trained means that we have a pre-trained model on the public dataset, and we try to fine-tune it locally. And FedD is our method. So we can see that from this result, we know that compared to training local models in isolation, FedD improves context FID by 79% on average and the correlation score by 62%, showing that our framework can produce much more realistic and structured time series. And what's notable is that FedD performs almost as well as a centralized training, even though no raw data is ever shared. That is quite surprised because it give evidence that the cluster, the coordinator and the clients are learn something from each other without sharing any real data. So to summarize, FedD is the first federated generative model to explicitly address both feature and temporal misalignment in time series data. By combining diffusion models and data distillation, we enable collaborative learning without sharing raw data or model weights. And in the future, we aim to expand this framework to even more complex multi-resolution time series, incorporate differential privacy guarantees, and reduce communication costs in real-world deployment. Yeah. I think that's all. Thank you. And if you have any questions, I'm so happy to answer.
Yeah, I think super interesting work, and I think the results are really amazing. So I have some questions, but again, if the audience has questions, feel free to ask them or drop a message and I will try to read them. So my first question was, so you mentioned that the distiller has a public data set. It is trained on a public data set.
Yes.
My question is, how does the choice of this public data set relate to the actual task you want to do? I guess it would matter if the time series is some financial data or if it's some, I don't know, sensor data, right? Or it doesn't matter.
Yeah, I understand. It must relate it to what you are doing. So in our case is that like some bank, some hospital, like you want to have a model, but you don't have much data and you want to learn something from the public data set. So you need to find a data set that fits your task. The domain has to be the same.
Oh, I see. Okay. So for example, for the 5 evaluations you have, like stocks, ETTH, Mujuko, and so on, you have 5 public data sets. So you can do the pre-train. Okay.
Yeah.
Okay, interesting. So while you were presenting, I was looking to the paper and I saw that there is, in figure 3, there is a cloud at the top that you call the coordinator, and there is some data. That data that the coordinator has is exactly this public data set we are talking about, right?
Oh, yes. Figure 3, yes.
Okay, interesting. I'm curious because, for example, I'm more familiar with, horizontal FL and doing not time series, doing other things like, LLMs or image and things like that. And typically, one of the things to do is to study how it scales the system when you have more clients or more non-ID setups. Yeah. Did you evaluate? Yeah, can you tell us a bit how how big was your setup? How many clients were there? Is it realistic to evaluate 1,000 clients for this, or it's not so common yet?
So this is a very interesting question. So about the IID non-IID setting, it is wants to be a very hard problem in our thesis. Like, because we know the tabular data or some data, they have labels. You can use labels to get different domain, different non-IID data set. You can set them, but in time series is very different. We don't have labels. We need to find a way to set the labels. What we do is that we use some k-means and the PCA method to label the time series to make them as different as possible. Then we have the label. We can have some non-IID setting, and we also test it. I don't know if we put it. I remember we put it in the thesis, so you can have a check. Sorry, it's almost 1 year, so
No worries, no worries.
I
Yeah,
think
I mean, looks in the appendix there are a million of results, so probably it's one of those. Very interesting. Another question also like a bit related. How long does it take, for example, to run all these experiments? Given that this is time series data, my thinking when I think about time series is that you use small models, everything is fast, but I wonder if because of the, all the distiller pre-training that would take some time. So can you tell us a bit?
Yeah, so
compute.
Okay. So it depends on the backbone. The backbone we use is the diffusion TS. So it is the DIT based model. So it's a diffusion transformer model, right? So it's a little bit huge. And for each round, it will cost about 20 minutes. And you can change the backbone run. That depends on you. And because the distiller and the imputer only do the fine tuning on each round, so it not take many time to do this. The full experiment, like around about 50 rounds, something cost about 10 hours.
Okay, well, not manageable. It's not too bad.
Yeah.
Okay, interesting. I think this paper would be an amazing addition to the Flower baselines collection. So if you're up to it, we can maybe sync offline. We can support you on whatever you need to. If you're interested, I think it would be quite cool.
Thank you.
Okay, let me check if there are some questions. I don't see any on Zoom, but I'm gonna check very quickly on Slack or on all the platforms like X and so on. Very quickly, I will check. Okay, I don't see questions, but that's fine. I mean, we know your contact details, so if anyone is interested in learning more about your work or the previous speakers' work, like Christos or Eleni or Yang Gao, everyone is welcome to contact the speakers. So thank you again, Chen Rui. I think it was super interesting work. So now we are moving to the last part of the talk, this session today, which is going to be the outro. I'm going to share my screen in 1 second. Okay, so this is the end of the Flower Monthly for the month of July. The next Flower Monthly will be next month, which will be, as usual, the first Wednesday of every month. It will be the 6th of August, a Wednesday. So I'll see you there again with more updates from Flower. One small reminder, if you are excited about attending the Flower AI Day in San Francisco at the end of September, feel free to check it out in our website. It is a Luma event, so it's essential that you register if you're interested in joining. You can join as a student or as a industry leader or person. So yeah, we'll hope to see you there. And if you cannot make it on the 25th, we're going to be around for a week or so. So I'm sure there will be time to interact. So thank you, everyone. Thank you, all the speakers and all the attendees. And have a great rest of your week.